Welcome to The Explainer. Today, we're going to dig into one of the most elegant and powerful achievements in all of science, the moment that electricity, magnetism, and even light itself were all brought together under one single, absolutely beautiful theory.
So let's just jump right in with a question that had scientists scratching their heads for centuries. You've got these three invisible forces that literally shape our entire world. The static shock from a doorknob, the strange pull of a magnet, and the light that lets us see everything. What could they possibly have in common?
Well, the answer came from this guy right here, the Scottish physicist and mathematician James Clerk Maxwell. He just had this unique way of looking at the world that let him see a deep connection where everybody else just saw three totally separate things. And the thing is, before he even got around to unifying physics, Maxwell was already a giant in a bunch of other fields. He wasn't just a specialist, he was a true polymath. And his ability to pull ideas from different areas of science, that was basically his superpower.
I mean, just look at this list. It is kind of mind-blowing. He gave us the first ever color photograph. He figured out that Saturn's rings are made of tiny little particles. He laid the groundwork for how we understand gases, and he even got into the math behind control systems and chaos theory. So you see, this wasn't just some physicist in a lab. This was a mind that was reshaping science on all fronts.
But the big one, his masterpiece, the thing we're here to talk about, was so huge, so profound, that people compared it to the work of Isaac Newton. Just think about that. Newton unified the laws of the heavens and the earth with gravity, and Maxwell came along and did something just as massive for the forces that run our world.
And how did he do it? Well, not with some single, simple statement. He did it with a set of 4 interconnected and just mathematically beautiful equations.
Okay, so this is the absolute key insight. Maxwell showed that electricity and magnetism aren't really separate forces. They're just two sides of the same coin, different faces of this one thing called the electromagnetic field. And light? Turns out light is just a wave, a ripple traveling through that very same field. Incredible.
All right, first up is Gauss's law for electricity. Put simply, this one just tells us that electric charges, like a positive proton or a negative electron, create an electric field all around them. The field lines just flow out from the positive charges and go into the negative ones. Pretty straightforward.
Now, equation number 2 is Gauss's law for magnetism, and this is where we see a huge difference. It basically says there's no such thing as a magnetic charge. You can't have a magnetic monopole. You can never ever have a north pole all by itself or a south pole all by itself. Magnetic field lines always loop back on themselves. The third equation, Faraday's law, this is where the magic really starts to happen. It shows how a changing magnetic field, like when you move a magnet back and forth through a coil of wire, actually creates an electric field. It gets the electricity flowing. This is the entire principle behind how we generate power.
And then the fourth one brings it all home. Ampere's law, with Maxwell's brilliant little addition, shows that an electric current creates a magnetic field. But, and this was Maxwell's crucial insight, a changing electric field also creates a magnetic field. It's this perfect symmetric dance between changing electric and magnetic fields that allows light and radio waves and all of it to travel through the emptiness of space.
So this theory is beautiful and all, but it's also super practical. And that brings us to a really common question, a puzzle that trips up a lot of physics and engineering students. If Maxwell unified the magnetic field, why on earth do we use 2 different letters for it?
Yeah, we're talking about the B field and the H field. They both have to do with magnetism. They're definitely related, but they're not quite the same. So why make things so complicated? Well, it turns out it's not a complication. It's actually a very clever simplification that's incredibly useful for engineers who have to work with real-world materials.
All right, think of it this way. The B field is the real deal. It's the total, fundamental magnetic field, the one that actually governs how charges move and exerts force. It's the whole picture. The H field, that's more of a handy tool. It lets engineers focus only on the magnetic field they're creating with their electric currents, and it neatly ignores how the material itself is reacting for a moment. It just makes the math way, way easier. So what connects them? The material, the stuff you're actually putting in the magnetic field. The difference between the B field and the H field is this thing called magnetization, or M. It's just a measure of how the material itself responds. And this simple little equation right here, B equals H plus M, it perfectly and elegantly ties it all together. You know, this whole unification thing, it wasn't just about closing the book on some 19th century physics problem. Nope. What Maxwell did became the foundation for pretty much the next century of physics and technology. It changed everything.
And get this, Maxwell's equations didn't just describe the world as he knew it, they predicted things that hadn't even been discovered yet. His math predicted that light was a wave and calculated its speed, and it also said there had to be other kinds of invisible waves. Sure enough, a couple of decades later, Heinrich Hertz discovers radio waves. And then, in 1905, these same equations became the absolute bedrock for Einstein's special theory of relativity.
I mean, don't just take my word for it. The great Albert Einstein himself said that Maxwell basically drew a line in the sand. There was physics before Maxwell, and then there was a completely new world of physics after him.
And he said it again, even more directly. He made it crystal clear that his own revolutionary ideas, the ones that changed how we think about space and time forever, came directly from wrestling with the consequences of Maxwell's equations. And really, that's what physics is all about, right? This constant search for unification. Maxwell brought three forces together into one. Later on, physicists managed to unite that force with the weak nuclear force. The quest is still going, which leaves us with one big, exciting question. What fundamental forces are still out there, waiting to be unified, and who's going to be the next Maxwell?